Circuit Notes Part 2. Today we're going to look at schematic diagrams. Schematic diagram is just a fancy term for circuit drawings. I'm going to start off with some symbols. Flat line is a wire. This one looks like a light bulb because it is a light bulb. This one is a symbol for a battery, and the longer side here represents the positive terminal of the battery. The smaller side represents the negative terminal of the battery. During the last lab, I had you put two batteries end to end, and you always hook batteries plus to minus when they're end to end. So this is the symbol. We call that a double battery, where we hook the plus end of one battery to the minus end of the other battery. So we end up with one double strong battery. Their voltages actually add together. This is the symbol for a resistor, and we can actually use it for any appliance. Anything that uses electricity, could be a fan, could be a lamp, could be a laptop. They all can be represented with a resistor because everything has a resistance to it in an electrical circuit, except for a wire. This one is an open switch. This one is a closed switch. Then for measuring our currents, we have this one is called an amp meter. It measures the current. And this one is a voltmeter. It measures our potential or potential difference. All right, rules for drawing our circuits. We need to have straight lines only, square corners only, no curved lines, no diagonal lines. So our first circuit would be a series circuit. We're going to start with an empty box, and each component goes on one side of the box. We usually put the battery on the left side with the positive at the top, and then each component, we try to put one component on each side, so we'll just do two light bulbs here, and then your last side will just be a wire. So we have straight lines, square corners. For a parallel, we're going to start with two parallel lines with nothing on them, and all of your components are going to go on vertical lines in between them. Again, we want the battery on the left side with the positive on the top, and then this time we'll put our two light bulbs, each one on a vertical line from top to bottom. Normally, your parallel line should end at the first light bulb here. Occasionally, I'll have a student draw their two parallel lines too long, and the question is, can we connect these? The answer is absolutely not. We never connect an empty line from top and bottom. What you're doing, remember, an empty line is a wire. You're connecting a wire to the positive and negative side of your battery. What you're doing is creating an easy path for the electricity to go around. You just made a second junction here, by the way, but the current is just going to go round and round and round the easiest path, and it's never going to bother to go through the other two light bulbs because those paths have resistance on it. Those aren't easy paths anymore. This is called a short circuit, and what it's going to do is, if it's just a battery light bulb circuit, it's going to burn your battery out. The light bulbs are not going to turn on, and the battery and the wires are going to get hot. If this was a circuit in your house, that heat is going to get so hot it'll catch on fire and burn your house down. The short circuits are the reasons why we need to have circuit breakers or fuses in our electrical boxes. So what do we need to know about a series circuit? For a series circuit, there's only one path for the current to follow. So it's the same current that goes through the entire path, but there's a different potential for each component inside the circuit. So we'll take the same drawing that we did before, and I'll put some resistances on the light bulbs here. The first thing we need to do is calculate what is our net resistance. The total resistance here, when they're in series, they add together. So we have a total of 15 ohms for our net resistance. And once you calculate that, what I can do is remove these from the circuit and replace them with a resistor of the same resistance. We call it an equivalent resistance. We use this drawing with the battery and the equivalent resistance to calculate what is the current going through this circuit. The The total current is the total volts divided by the total resistance. So we had 12 volts, and our equivalent resistance, or our net resistance, was 15 ohms, so that comes out to 0.8 amperes. So there's 0.8 amps going around this circuit, and that means there's 0.8 amps going through each component on my series circuit over here. Now, because it's a series circuit and there's one path, that electricity has to go through the first light bulb to get to the second one. So if the first light bulb burns out or gets unscrewed, the current stops and can't make it to the other light bulb. Likewise, if the second light bulb burns out, since the current can't continue on back to the battery, it won't continue out the other side of the battery, and there will be no current flowing at all. Once we have our net resistance, we can calculate our potentials. We said it has a different potential for each of the components. The battery is creating the potential. It creates 12 volts, and each one of these light bulbs is going to use up some of the 12 volts. So we can calculate this by using Ohm's law of V equals I times R. We're going to take our current that we calculated, 0.8 amps, and multiply it by our 10 ohms, and we'll get 8 volts. So of the 12 volts that the battery is creating, 8 volts is used by this light bulb. That means this one is going to use whatever's left over, which would be 4 volts. We should actually calculate that. The voltage that this light bulb is going to use is going to be the 0.8 amps times the 5 ohms, which is, of course, 4 volts. So we have one current going through here and a different voltage for each component. We've got 12 volts, 8 volts, and 4 volts. All right, what do we need to know about a parallel circuit? Parallel circuit has multiple paths. There's more than one path. The potential is the same for all of the components, but they have different currents. So it's backwards from the series. Series had the same currents, but different potentials. So we'll do the same drawing here, and we'll use the same numbers just for comparison. First thing we have to do is find the total resistance, and because it's in parallel, we're going to add by inverse. So this is 10 inverse plus 5 inverse, and the shortcut on your calculator, you're going to do 10, hit the inverse button, then plus 5, hit the inverse button, and equals, and it's going to give you number 0.33. But you need to be careful because you just calculated 1 over the net resistance. If we want the net resistance, we have to inverse one more time. So hit inverse again on your calculator, and it'll tell you the net resistance is 3.3. Instead of writing all of this out or writing out what you're typing on the calculator, we just write it this way. We do the calculation on the calculator. So we have 1 over 10 plus 1 over 5 equals 1 over 3.3. So this is our net resistance, and therefore we can make an equivalent circuit that has our 12 volts and the equivalent resistor of 3.3 ohms. So we're going to use this drawing to calculate the current going through our circuit. And the current that goes through the battery is always I1, and it's the voltage divided by the total resistance. So I got 12 volts divided by 3.3 ohms. I got 3.6 amps. Is the current that's coming out of the battery here. I'm going to go ahead and draw in like this, and I'm going to label that I1. I1 is always the current that comes through the battery. This point right here is a special point. It's called a junction, and the junction is where the current is going to split into two different paths. Remember, that is the definition of parallel. It has more than one path. So at the junction, we see we're going to have current 2 go down this way and current 3 go around this way. Now, logic tells us if this current is splitting into two currents, then current 1 has to equal current 2 plus current 3. So these two values have to add up to current 1. Down at the bottom, you can see there's another junction here, and this is where current 2 and 3 add together to make current 1 that goes back into the battery again. All right, so we calculated current 1. To find current 2, we're going to do the voltage from top to bottom divided by the resistance from top to bottom on line 2 here. So on a parallel, the voltage is the same for all of these. It's 12 volts, and we're dividing by 10 ohms is the resistance of line 2 here. So I get 1.2 amps. For current number 3, we can do the same thing, or I can do a shortcut. I know my 3.6 amps has to equal 1.2 amps plus what? I can subtract these two numbers to find current number 3. It's 2.4. Although it's probably better to actually calculate it. We have the voltage from top to bottom is 12 volts divided by the resistance from top to bottom on this line is 5 ohms. Gives me 2.4 amps. End of notes.